Great. Okay, so welcome everyone. We're very happy to revamp the series again. We will have a very full schedule for the next weeks. And today we're very happy to have Yoshitaka Hatta from BNL. Most of you know him, so he doesn't really need an introduction, but let me anyways say a few words. So Yoshitaka got his PhD from Kyoto University in 2004. Then he did a couple of postdoctoral positions, one at Riken BNL, then in Saclay. Then he became assistant professor in Tsukuba, where he eventually became associate professor, and then he moved to the Yukawa Institute in 2013 where he was an associate professor. And now he's in Brookhaven National Lab, where he's a senior scientist. And Yoshitaka is an expert on many fields of QCD, on hadron tomography, jets, TMDs, small x physics, spin physics. So we are very excited to hear from him today. And the topic is QCD spin physics with a particular emphasis with the EIC. So please, Yoshitaka, go ahead.
Right, thank you very much for the introduction, and also thanks for the invitation. I was asked to talk about the recent developments of the QCD spin physics on the theory front. And I suppose that the audience is not so familiar with the spin physics. So this is indeed an introduction and the overview of the recent progress. So instead of picking up one subject and going into details, so this is more like I try to pick up as many topics as possible in which I was involved. So here's the content of my talk. So there are 4 parts. First, I talk about the longitudinal spin. The main thing is basically the Jaffe-Manoha sum rule, the helicity distribution, and the orbital angular momentum. So that's the first part. And then in the second part, I switch to the transverse polarization, the phenomenon associated with the transverse polarization of the proton. And the main issue here is the single spin asymmetry. And I will talk about the origin of the single spin asymmetry in particular. Then the third topic is the generalized parton distribution function, the GPD. And so the main topic is the G-sum rule for the nucleon spin. And I talk about the challenges and the status of the field and the challenges in future, especially at the Electron-Ion Collider. And then last point is a bit exotic topic. It's about the nucleon electric dipole moment. And in fact, this has a deep connection to the proton spin problem, because dipole moment must be proportional to the spin vector. So there is a connection, and I'm trying to, and basically I will suggest a new way to constrain the electric dipole moment of the nucleon from the measurement of polarized high energy polarized scattering. So let me start with longitudinal spin polarization. So here's the proton spin problem. We have 2 basic facts about the proton. We know that the proton has a spin 1/2. It's a fermion. And also, at the same time, the proton is not an elementary particle. So from these 2 facts, we immediately conclude that the spin of the proton 1/2 is ultimately decomposed into the helicity and orbital angular momentum of quarks and gluons. So there is this Jaffe-Manoha sum rule, which says that the proton spin consists of the quark helicity delta sigma and gluon helicity delta g, and orbital angular momentum of quark and gluon LQ and LG. And there is another sum rule called the G-sum rule, which says that so it consists of 3 pieces. The first one, delta sigma, this is identical to the Jaffe-Manoha sum rule. And there is a kinetic and the orbital angular momentum of the quark, but this orbital angular momentum is different from the orbital angular momentum in the Jaffe-Manoha sum rule. So I use a different notation here. So I put the subscript to kin, which means kinetic orbital angular momentum. And there is a total angular momentum of the gluons. So for this, in the G-sum rule, you cannot decompose the gluon spin into the helicity and orbital momentum in the gauge invariant way. But in any case, so there are two ways to decompose the proton spin, and their relation is by now completely understood. And so the naive expectation is that, so delta sigma is 1. This is from the naive quark model. So basically the proton spin is just a combination of the spin of the quark. There are 3 quarks, and then it's just adding up the spin of the spin of the quarks. So one can actually measure this delta sigma from experiments from the polarized DIS experiment. So this is DIS, the proton and the lepton, or in this case, the muon, and both proton and muon are longitudinally polarized. And then you measure the asymmetry, you take the difference of the cross-section where the 2 lepton and proton spin are pointing in the same direction or the opposite direction. So you take the difference of this cross-section and take this form this ratio, AAL, it's the double longitudinal spin asymmetry. And then one can show that this ratio is proportional to the so-called G1 structure function. So you can measure this G1 as a function of Q square and X Bjorken. And then so you can experimentally determine G1 as a function of X, and then you integrate this G1 over X from 0 to 1. And then after some flavor decomposition, you can extract this delta sigma. And in this way, we know that the value of delta sigma is roughly about 0.3, which means that the quark helicity accounts for 30% of the proton spin. And the remaining part, the remaining 70% has long been a mystery. And this is which people call it the dark spin. Right, so in terms of this helicity distribution, there's been a very great progress in the last couple of years in terms of precision. So here I show a couple of examples. So there is this full loop evolution of delta sigma, which is, this is by De Flore and Voges, and this first plot on the left, upper left. And there is next leading order jet production in polarized DIS in order to access the Gluon helicity, which I talk next. And also there's a next leading order longitudinal spin asymmetry of W at weak, and also the 3-loop Wilson coefficient for this G1 structure functions. So these are basically the higher order calculation, which are usually done for the LHC observable, but nowadays these experts are looking into the helicity sector, which is observable in relation to the EIC. So I think this is a great movement in the field. So let me move on, come to this second entry of the Jaffe-Manohar-Sum rule. This is delta G, which is experimentally one can determine it by first measuring this delta G of X. This is the polarized Gluon distribution, the polarized Gluon helicity distribution, and integrate this function over X from 0 to 1. And so we now know the value of this integral in some limited region, kinematical region. And so this is basically the major achievement of the weak spin program. And from the experiment data, one can extract this quantity by using the global analysis. So there are 3 major leading groups doing this global analysis: DSSV, NFPDF, and JAM. And they, from at least from this limited range in X, for example, this DSSV 1 to 0.05, 0.05, and then the value is 0.2, which means that the 40% of the nucleon spin is coming from delta G from this X region. And you can see these 3 collaborations, the values are more or less consistent with each other. However, this is not the end. Of course, this is not the end of the story, because you have, in principle, you have to integrate it down to 0, right? X equals to 0. And but right now the experimental data limited, so it's instead of 0, it's 0.05, and there is a huge uncertainty from the small X region. And so that's why we need an electron-ion collider. So most likely, EIC would be able to determine the value of delta G with good accuracy. And because of this large uncertainty, there is a renewed interest in the community about what is the behavior of this helicity-dependent PDF at small x. So this is a very interesting subject on its own, and Yuri and his collaborator vigorously pushing in this direction. But in any case, the current status is that delta sigma is like 30%, and the delta G from the large X region is like 40%. And then the naive expectation is that maybe the remaining 30% of the spin simply comes from the yet unmeasured region in X, in the small X region. So maybe that's the solution of the spin puzzle. But that's not the case.
I have a question.
Yes.
Could you go back to the previous slide? So how much do these contributions depend on Q square? So here you show Q square is 10 GeV square, but how does this pi that you show, this distribution, change?
Well, so if you, I think if you increase the Q square, then delta G will increase. I don't have a plot, but that's okay. Just a qualitative. And yes, of course, the Q square dependence is well known. I mean, the Degraph splitting function is computed to 3 loops, so we can study this Q square dependence. I think, by the way, all this global analysis is, I think, the next feeding order.
Mm-hmm. Yeah, I just wondered, just to get a sense if it changes significantly with Q square, or if it's just a small change of just a few percent.
Well, maybe you can get idea from this plot. So this is not delta G, but delta sigma, and there's a function of Q square, and yeah, so this is really going to very low Q square. It's less than 1 GeV. So maybe you have to interpret it carefully. But in the large Q region, the Q square dependence is it's a bit weak. But maybe this is specific to delta sigma, because it is known that the delta sigma has a very weak Q square dependence, at least in the large Q region. And I think it's more rapid, it's more steep for delta G, but I cannot show you. I don't have the plot right now.
Okay, thank you.
All right, so as I said, maybe the naive expectation is that the remaining 30% of the spin may simply come from the X less than 0.05 in this delta G. But that's not the case, because we are forgetting something very important. There is actually an elephant in the room, and that's the orbital angular momentum. So it is actually, it's no secret that experimentally we know nothing about orbital angular momentum, and literally nothing. And there is no measurement in the past, and there is no plan in the future. So we know nothing about orbital angular momentum. But of course, this doesn't mean that the orbital angular momentum is unimportant. And in fact, there is a reason to believe that OAM is significant, especially in the small x region. So here's a very simple argument. So let's suppose that, let's imagine that there's a very energetic clock is traveling at the speed of light, as you can see in this cartoon. And this clock emits a very soft gluons. So this momentum fraction x, and x is very small, like 10 to minus 3. Then, of course, nothing happened to the clock, because clock doesn't even realize that it has emitted this gluons. So in particular, the helicity of the clock is unchanged. It doesn't change. And then it means, then because of the angular momentum conservation, the total angular momentum of this emitted gluon is 0. So the helicity of the gluon must be completely canceled by the orbital angular momentum of the gluon. So, and you can see this, so this is a very physical argument, and you can see that if you look at this Degraph evolution of the helicity and orbital angular momentum, and you can see there is a sign difference from the mixing part of the clock helicity distribution function. So, so we have reason to believe that if you go to the small x region, then helicity and orbital angular momentum cancels with each other. And this is, one can actually make this statement more precise. So this is a work that I've done with Fen. And so if this delta G of x goes like 1 by x to some power, where alpha is between 0 and 1, then under fairly general assumption, then one can show that this orbital angular momentum of gluon behaves, goes like this proportional to delta G with this coefficient, which is larger than 1, and there is this crucial minus sign in front. So if you go to the small x region, then orbital angular momentum and the helicity cancel each other. And on the lower left plot, you can see the one loop D-graph evolution of delta G and orbital angular momentum as a function of log 1 over x. So if you go to the right in this plot, then it goes to the small x region. And here you can see almost perfect cancellation between delta G and the orbital angular momentum. So, so the conclusion here is that there might be a sizable sizable contribution to delta G from the small x region. However, there will be even larger orbital angular momentum from the same x region with an opposite sign of this cancellation. And so, just measuring delta G will not be a solution of the spin puzzle, and helicity is only half of the story. It's actually half of the half. And then big question for us is that can the EIC seriously address the orbital angular momentum? And that's very tough question because so far there's no measurement and no proposal of experimental observable until a few years ago. But in order to explain that, I have to introduce something new. This is a so-called Wigner distribution function. So the Wigner distribution function is basically the ultimate phase space PDF. So this is a generalization of PDF such that it includes the dependencies on the transverse momentum K-perp and also the transverse coordinate V-perp. So this is a 5-dimensional object. It's the most fundamental parton distribution function, the single particle distribution in the proton. And actually, because this function depends both on the transverse momentum and on transverse coordinate, then you can naturally define the orbital angular momentum simply by computing this cross product between B cross K, which is the classical definition of the orbital angular momentum, weighted by this phase space Wigner distribution function. And it turns out that this is a satisfactory definition of the orbital angular momentum. So, the measurement of the orbital angular momentum is almost equivalent to the measurement of the Wigner distribution function, which is unprecedented challenges. Nobody has ever measured the Wigner distribution function. So that's a very challenging problem. But this is an interesting question on its own because you can see the effect of the Wilson line, the impact of the Wilson line in this definition of. So this Wigner distribution function, this is a bilocal quantity. So this clock operator is defined at different points in the in the transverse plane. So you have to connect these 2 points by the Wilson line, and this choice of the Wilson line is actually not unique. So if you go to the right cone infinity and then comes back, then what you get from this definition is orbital angular momentum that is relevant to the Jaffe-Manhar sum rule. So here, instead of the covariant derivative D, I have something different. So this is a non-local operator. So this is a gauge invariant definition of the Jaffe-Manhar orbital angular momentum. But instead of going this roundabout way, you can just go directly from this point to that point. And you can do that. And if you do so, then what you get is the orbital angular momentum in the G-sum rule, as shown by these people. And the difference matters, actually. And there is a measurement by Michael Engelhardt on the lattice QCD, where they tried 2 different configurations of the Wilson line, and they indeed find the difference on the resulting orbital angular momentum. So this is a very interesting interplay of the phase, this quantum phase effect of the Wigner that can be seen in this Wigner distribution function. And so, and in fact, in the last 5 or 6 years, there is indeed a proposal about the measurement of the orbital angular momentum, and this is which can be done at the Electron-Ion Collider. So this is a longitudinal single and double spin asymmetry in diffractive dodges. So there is a work by Ji Yuan Zhao in 2016, they proposed a single spin asymmetry. And this year, me and my collaborators proposed a double spin asymmetry. And so the basic idea is to compute this diagram at the twist-free level with both polarized proton and electron are polarized. And then blob here is actually the Wigner distribution function. And so if you calculate this diagram to twist-free accuracy, then you find this amplitude is proportional to the orbital angular momentum. So in the case of double spin asymmetry, the resulting formula is like this. You can see on the bottom. And so this is a spin-dependent part of the cross-section. And this, you have this cosine angular modulation between the lepton angle and recalling the proton angle. And sorry, I forgot to say that we have to measure this Diejet system in the forward direction. So this is the exclusive Diejet production in this polarized scattering. And we have actually two competing contributions. One is from because you calculate the interference between this amplitude. So in the amplitude you pick up this unpolarized gluon PDF, and then the complex conjugate amplitude you pick up the contribution from the gluon helicity and the gluon orbital angular momentum. And depending on the value of Q perp, which is transverse jet momentum, then this orbital angular momentum and the helicity add up or cancel each other, because, as I said, there is a cancellation between delta G and orbital angular momentum. And you can test this theory prediction by measuring this observable as a function of the jet transverse momentum Q perp. So you can, for example, this is a numerical estimate of the cross section, which is actually a prediction for the EIC. And you can see the at low value of Q square, you can see the orbital angular momentum and the helicity tend to cancel each other. They have the opposite sign here. But if you go to large Q square, and then they have the same sign, and that's because of the this factor, which is depending on the transverse momentum, and mu square is depending on the Q square of the larger photon. So in any case, this is but this is just the beginning. This is a fast prediction of orbital angular momentum at the EIC, and in order to be more quantitative, at least in order to make this prediction, we need to know this delta G at small x, which has a huge uncertainty, as I said. So if you want to if you want to measure the orbital angular momentum, then we need to know this delta G precisely at small x, and this is the future challenges of the field. All right, so that's all for the longitudinal polarization, and I move on to the next topic, and this is the transverse spin. So the main observable for the transverse single spin transverse polarized spin is a single spin asymmetry. So this is a collision between two hadrons, and one of the hadron, usually proton, is transversely polarized. So the spin direction is pointing in perpendicular direction to the direction of the motion. Then you count the number of particles produced to the left of the left-hand side and the right-hand side, and they are different. So there is a sign modulation, the sign correlation between the direction of the spin and the direction of the produced hadron. So this is called the Shiver's asymmetry. And so experimentally, people usually take this ratio A sub n, which is basically a difference of the cross-section on the left and right divided by the averaging. And there's a very long history of the experimental measurements since the 70s. And in some cases, this asymmetry can be as large as 20 or 30%. So it's a really big effect. And we want to understand why from QCD. And so, so this is a theory for the single spin asymmetry. So we are looking for the part of the cross section which is linear in the spin. So you can see it's delta. We are looking for this correlation which is linear in the spin vector, and that's non-trivial because the cross section is a square of the amplitude. So it's non-trivial to get a linear dependence on the spin. And the only way to do that is to look for the interference terms. So for example, this diagram. So the diagram on the left-hand side of the cut and the right-hand side of the cut are different. However, if you naively compute this diagram, then you get 0, because this diagram is, if you compute it naively, then this diagram is purely imaginary. So if you add the complex conjugate, then the cross, then you get 0. So in order to get non-zero result, then an extra factor of I is needed to make the symmetry non-zero. And so we actually know different origins of single spin asymmetry. So for, the simplest way to get this extra factor of I is to look at the pole, pick up the pole of the propagator. So if you have a quark propagator with momentum k, then there is an I epsilon term in the denominator. So basically pick up this delta function piece, and that gives an extra extra factor of I to make the cross section real. And this is called, so what you get from this diagram is that, you get a symmetry proportional to this quark-gluon-quark correlation function. So this is a twist-free effect. And there are actually different ways to get this I. So this is the one that I just explained is called the soft gluonic pole, which is related to the so-called Chu-Stammer function. This quark-gluon-quark function is known as the F11 of TRF Chu-Stammer function. And there's also you can also get the I from the fragmentation function. So if you go to the 2-3, then the fragmentation function itself becomes complex. So you get the I from the fragmentation function. So that's another origin of the single spin asymmetry. And if you go to the KT factorization or TMD factorization, then there is an interesting TMD called the Shiva's function, which has this spin on the transverse momentum correlation. So this Shiva's function can be an origin of the single spin asymmetry at low PT, where the TMD factorization applies. And so now the question is that because there are so many different origins, then the question is which one is most important. So you have to, in order to answer that, you have to do the global analysis. And this is a work, this is the most advanced group. It's a paper from 2 years ago, where they did a simultaneous fit of many different experimental data, assuming that soft gluonic pole and twist-free fragmentation functions. And they obtained this successful fits of all these experimental data. And the conclusion right now is that at the moment, the only viable way to generate a 10% asymmetry seems to be the twist-free fragmentation function. So as I said, this twist-free fragmentation function can be a complex function, so you can get the I from there. And this seems to be likely the origin of the large single spin asymmetry. And this is a good sign because this twist-free fragmentation function couples with the transverse distribution function, which is related to the tensor charge. So there is an interesting discussion whether this tensor charge obtained from the single spin asymmetry data is consistent with the lattice calculation. So this, which is shown on this lower right plot. All right, so that's the, and in the future, if you go to the EIC, then you can add more data from in this sheetless data. So right now you can see there are only low energy experimental data like Compass and Hermes and JLab. And so you can add more data points at high energy, and that's, then you can do this global analysis more precisely. But before that, I want to bring up new development in this field, which goes back to this old-fashioned perturbative QCD contribution to the single spin asymmetry. So I suppose you are not in this community, so let me tell you a story. So in the QCD spin physics community, there is a well-known prejudice which goes like this. So the perturbative QCD contribution to single spin asymmetry is negligible. It's completely negligible because it's proportional to the quark mass. So this A sub n, so there is a rough estimate of this asymmetry A sub n from perturbative QCD, which is proportional to MQ. It's a current quark mass. It's a current quark mass, so it's like a few MeV, right? So this prediction was made in the 70s, and for 40 years, nobody challenged this prediction. But in fact, this turns out to be incorrect. So there's actually no real PQCD calculation beyond this parametric estimate for 40 years. So we recently considered this, revisited this issue to get this perturbative. So this is a diagram to be calculated in perturbative QCD. So this two-loop, this hard part, so there's a hard part and soft part. And the hard part is the same as what was proposed 40 years ago by Ken Pumphrey Repco in the case of series in DIS. However, the soft part is different. So these authors didn't think about the soft part, but in real QCD, the soft part associated with this two-loop diagram is a function called GT. And here's a definition of GT, which is similar to the polarized PDF, but this gamma mu is the transverse index since the proton is transversely polarized. And you can see this the spin vector is normalized to the proton mass. So this GT comes with the proton mass instead of the quark mass, and that gives 100 times larger symmetry compared to this naive estimate. And so we did this calculation. We actually need this GT function. So there are actually two diagrams. So one diagram on the left, this is proportional to the GT. And there's another diagram which contains the free parton exchanges between the soft and hard part. And you have to sum these two contributions, otherwise the gauge invariance is lost. And this is this calculation of the cross section in a different channel. You don't have to look at this, just to show you that we did this. And I want to emphasize that the quark mass plays no role in this calculation. So the quark mass is simply 0, but we get a non-zero result for the single spin asymmetry. And so here's the parametric estimate. So we do this one-zero-check approximation, which says that this GT function is given by is proportional to the quark helicity PDF. It's a particular moment of the quark helicity PDF. So after this one-zero-check approximation, then the A sub n goes like is proportional to the nuclear mass times this polarized quark PDF divided by the unpolarized quark PDF. So this is in the case of CDS, we have PT in the denominator. And in the case of PP collision, we have S in the denominator. But in any case, this is different from this old 40 years old prediction 40 years ago. And so this old formula is simply wrong.
I have a question.
Yes.
So if it's a purely perturbative calculation, how does the mass of the proton show up?
Well, like I said, this GT is proportional to S perp, and S perp is proportional to the proton mass.
But
okay, so you never calculate the cross section 100% perturbatively, right? It's always a convolution of hard part and the soft part, right? Mm-hmm. And the soft part in this case is GT, and GT is proportional to GT comes with the proton mass.
I see.
And this was missing in this old calculation, and this old argument. Which
so they didn't consider the soft part?
This paper, there is no real calculation. It's just a parametric argument, and I mean, nobody thought about this. What is the soft part associated with this? So we did that. All right, so this is a correct estimate. This is a correct parametric estimate of S of n, which was to be used in going forward. All right, so we get a similar contribution from the gluon channel. So there is an analog of GT in the gluon channel, which we call the G3T. And again, if I do the one-zero-check approximation, then I get the S of n proportional to the delta G times hard part and unpolarized twist-to PDF, twist-to fragmentation function. So these are all twist-to distribution, and that still gives the transverse single spin asymmetry. And this is another origin of the single spin asymmetry, which might be important for the single spin asymmetry of heavy like John. So we did this. We did a numerical estimate also for the Electron-Ion Collider. So it's the prediction for the EIC, and we find that up to 2% asymmetry for the 3 types of harmonics. The first one is the Chivas asymmetry, which is the top plot. So I get 0.02. That's a 2% asymmetry in S of n. And we also find a few % asymmetry in other 2 harmonics like sine phi s and sine 2h 2 phi minus phi s. And I want to emphasize that there's no free parameter because the only thing that is involved is the twist-2 PDF and twist-2 fragmentation function. And it actually, if you compare this, the magnitude of the asymmetry to other mechanism of other traditional mechanism of single-spin asymmetry, like the Shiba's function, they're actually comparable. However, we find that Collins asymmetry is negligible. And for that, we probably need a twist-free fragmentation function. So there's no, yes, for that part, perturbative QCD has, you simply cannot compete with the fragmentation function. But in the Shiba asymmetry channel and other symmetry, we get 2%, a few percent asymmetry, which is comparable to the other mechanism of asymmetry. So that should be taken into account when you go to the EIC. And there is actually another paper from the Germany group where they calculated the longitudinal single-spin asymmetry from the perturbative QCD using this similar two-loop diagram. And that can also be tested at the EIC. So at the EIC, maybe we can study this single-spin asymmetry from perturbative QCD in a systematic way. And that's important because it affects the extraction of the Shiba's function, for instance. And all right, so this is for the collinear factorization approach. And we also have a result for the TMD case where we find a bunch of new contributions. So the first term is the Shiba's asymmetry. And the first term on the third line is the Collins asymmetry. And the first term on the second line is the analog of this mechanism in the TMD region. So instead of GT, I get the G1T, this is a TMD. And so this is a TMD analog of this two-loop mechanism. And the point that I want to make here is that the Shiba's asymmetry is not the same as the Shiba's function. So the Shiba's asymmetry is the sine phi correlation between the spin and the hadron momentum, but that doesn't come from Shiba's function. It doesn't only come from Shiba's function. There can be many other origins of Shiba's asymmetry. So that's something which one should worry about. All right, so that's for the single spin asymmetry for PP and in DIS. And now I want to mention another interesting process. This is the single spin asymmetry in proton nucleus collision. So because there's been a measurement at RIC. And so the interesting question here is that how does A sub n depends on the mass number of the nucleus. So this is the proton nucleus collision, and the proton is transversely polarized, and then count the number of pions produced to the left and the proton to the right. And if you go to the forward region of the polarized proton or the backward region of the nucleus, then you are sensitive to the small x region of the nucleus, and then you might be able to probe the effect of the gluon saturation. And so there's been a measurement at RIC, both by the Star and Phoenix collaboration, and there is actually a tension between these two results. So the Phoenix collaboration find that this A sub n goes like a to the minus 1/3. And you can see this is a PP, the P aluminum, and P gold as a plotted as a function by a to the 1/3. And so you can see there's a big A dependence. On the other hand, the Star collaboration basically found no dependencies on A. And they are not actually inconsistent. They are not inconsistent because they made a measurement in slightly different kinematics. There's no overlap in the kinematics, but however, the results are qualitatively different, and this is a very striking. So there's been a theory attempt to explain this. So first, I think the first paper of this kind was Boa, Dumitru, and Hayashigaki in 2006, where they used the KT factorization, basically the Shiba's function, to explain the A dependence of the A sub n. So this is a formula within the KT factorization, which says that A sub n is proportional to the derivative of the unintegrated gluon distribution function of the nucleus. And so, and if you assume this Gaussian form in the saturation region, then you basically, by taking a derivative, you bring down this factor of 1/QS squared. And since QS squared, the saturation momentum squared goes like a to the 1/3, then the prediction here is that the A sub n behaves like a to the minus 1/3. And that seems consistent with this Phoenix result. And there's also work by Fen and Zombo about the contribution from the Collins fragmentation function, which has a similar conclusion. However, but we are very surprised by this star collaboration star data, which shows no dependence on A. So we basically revisited this theory prediction back in 2016. Where actually this is a theory post-diction because the preliminary study that came out like in 2015 or so. So we are motivated by the experimental data. So so what we did is basically dump the KT factorization approach because it's questionable in proton-nucleus collision. So instead we use the collinear framework, which is actually a hybrid framework. So we use the collinear PDF for the proton and the KT-dependent PDF for the nucleus. And so the first line is a contribution from the Chu-Sterman function. This is a soft Green pole contribution. And so the first line of the first equation is basically the analog of this KT factorization approach. So this term goes like a to the minus 1/3. However, in the second term, we get a different contribution, which is proportional to the Green distribution function. It's not a derivative of the Green distribution function. And this term goes like a to the 0. So there is actually a contribution which is constant in A. And the same thing happens in the fragmentation channel, which is probably the more important contribution to single spin asymmetry according to this global analysis. As I said, the fragmentation function is right now the most promising way to explain the asymmetry. And for that part, we get different contributions. So we get 3 terms, which each has a different dependencies on A. And right now, probably this last term is according to the analysis of proton-proton, this last term is probably the most important term according to this global analysis. And this term behaves like A, it's constant in A. And more recently, there is a work by Gambart where they also studied this first term on the last line. And this term might not be negligible. And this term has a different A dependencies. So by measuring this A dependence, one can get a handle on which term is more important. And we also did a numerical simulation of the effect. And you can see this is a blue and reds are the PP and the PA. And you can see that there's not much strong A dependence at least in this PT region. So, however, the problem is that the star collaboration measure the PT in the largest PT region. So the PT is between 1.7 and 6 GeV, which is large compared to the saturation momentum of the proton, of the nucleus, sorry. And in order to really see this suppression, then you have to go to the PT less than the saturation momentum, which was not possible in the old measurement, but this will be done in the new measurement after now the star people can do this because of the forward upgrade. And maybe there will be a new data in the next 1 or 2 years. All right, so let me come to the next topic, that is the generalized parton distribution function, GPD. This is basically the known-forward generalization of the parton distribution function. So here's the definition: the incoming proton and outgoing proton have different momentums of P and P prime, and the difference is the delta, and you can define the GPD. So you have 2 GPDs, it's H and E. So these are the leading twist GPDs. And the second term is special, it's because of the known-forward kinematics, which is explicitly proportional to the momentum transfer. And so you can think of this GPD as a kind of densities for the form factors. So if you integrate this H and E over X, then you get the electromagnetic form factor, the Dirac and the Pauli form factor F1 and F2. And if you first multiply by X and integrate over X, then you get the so-called gravitational form factor. It's a matrix element of the energy momentum tensor. So that's a very exciting topic right now, but I don't, of course, this is not the topic of this talk, but there's been lots of discussion about the gravitational form factor in recent years. And the physical interpretation of this GPD is that if you take the Fourier transform of this GPD with respect to delta and go to the transverse coordinate space B perp, then you can see the picture, the image of the parton distribution in the impact parameter space as a function of X. So that's the physical interpretation, how the partons are spread in the impact parameter space. Now, this GPD is interesting because it is related to the G-sum rule, which is another way to decompose the proton spin. So basically, the second moment of GPDH and GPDE is related to the total angular momentum of quark and gluon. So this is the sum of the helicity and the orbital angular momentum. So this is a G-sum rule. And you can actually extract this H and E from the deeply virtual completon scattering. So this electron-proton scattering, the final state consists only of the real photon and recalling the proton and maybe the electron as well. And so you basically measure this completon form factor, completon amplitude, and that this is given by the convolution of this GPDH times this complicated kernel. So this is on the lower right corner, you can see the kinematic coverage of the DVCS at the Electron-Ion Collider versus the existing data points. And you can see the EIC offers an unprecedented kinematical coverage for DVCS and other exclusive processes which are sensitive to GPDs. So this EIC will be the dream machine for the GPD studies. This will be a new era of GPDs in the coming approaching. So here are some theory challenges, the status and the theory challenges for the EIC. There's been higher order, very impressive work by Brown and his collaborator about higher order PQCD calculation. So the splitting function has been calculated to 3 loops, and the coefficient function has been calculated to 2 loops. So this is a very recent paper. And these are basically the ingredients for the next leading order global analysis. However, the community, maybe this is too much. The community is currently struggling to come up with the next leading order global analysis, and there is a work effort by Krejmir and his collaborators. And on the other, and also there is lots of effort to calculate GPD and the lattice QCD. There's been, so this X-dependent PDF can be calculated, is calculable in lattice QCD these days, and there's been lots of effort in PDF, but also in GPDs as well. And also this GPD, there's been a lot of discussion about the extraction of the gravitational form factor, in particular, the so-called D term, in other words, it's the pressure distribution in the proton. But this is not related to the spin, so I'm not gonna go into the details. And I think from my viewpoint, the most important challenge about this GPD is the extraction of the GPDE, which is defined, which is the second term here, and that's because if you look at this G-sum rule, then first term H is related to the usual unpolarized gluon distribution function. So the forward limit of this GPD is the ordinary unpolarized gluon distribution function, which we know very well. So the only non-trivial ingredient in the G-sum rule is this GPDE, and that's very difficult to measure even at the EIC, especially the gluon GPDE, EG of X. So maybe so instead of looking at this DVCS, maybe we should look at other processes which are more sensitive to this gluon GPD. And one of this might be this measurement of the single spin asymmetry, exclusive single spin asymmetry of J psi in the electron-proton scattering. And so there's this process will be measured by the star collaboration in the next year or next 2 years. And basically, this is an exclusive single spin asymmetry. You have proton and J psi in the final states, and you basically measure the asymmetry with respect to this transverse plane. And this asymmetry, since this is exclusive, the amplitude is proportional to the GPD of H and the interference between GPDH and GPDE. And this will be measured, and this will be the projection of this of the S sub n at the star. And this is projection of the error. So they're trying to reduce this large experimental uncertainty with this new forward detectors. Now, one thing one can ask is that, in fact, indeed, if you measure this process, then you can get a handle, or you can get information about how this EG of X behaves at small x. So how does but let me ask a more general question. How does the GPD behave if you go to the small x region? And for the helicity non-flip GPD, the GPDH, then the answer is well known because for the limit, and this is basically proportion. This is basically the same as the unpolarized gluon PDF, and we know this unpolarized gluon PDF behaves like 1 over x to some power, this famous number 4 times log 2. That's called the BFK Pomeron, because this TMD for this unpolarized gluon satisfy the BFK equation, and the solution of the BFK equation is well known. However, there was not much discussion about small x behavior of this gluon GPDE, and this is, well, basically there has been no previous work, and then question is, what is the power of this small x behavior, 1 over x to which power is this? So in order to answer this question, you have to introduce KT in PDF, but E is a GPD, and so if you introduce a KT in GPD, then what you get is a GTMD, or in other words, the Wigner distribution function. So in order to answer this question, we need to understand the Wigner distribution function, which is possible only in the last few years, which became possible only in the last few years. And that's why nobody addressed this question until now. But in my last paper, most recent paper, James Zhou and I derived the small x evolution equation for the unintegrate for the GPDE. And this is an equation which is the first term, and so the first term is identical to the BFK equation. So the conclusion here is that this GPDE behaves like 1 over x2. It's exactly like the BFK Pomeron behavior. It's proportional to the unpolarized gluon PDF. And also you can see this nonlinear, there's a nonlinear term from the gluon saturation. And if you take that into account, and then you can show that this GPDE gets saturated if you go to the small x region in the same way as the unpolarized gluon PDF. And this might be important phenomenologically because this x times E behaves like diverges if you go to the small x region. And that means that there may be a significant contribution to the G-sum rule from this small x region, because you have x times E in the integrand, and this function behaves like 1 over x to some other power. So that, and you can actually, in fact, this experimental data of this A sub n is sensitive to the small x region of this GPDE, because you can roughly speaking, this A sub n is proportional to the ratio, it's basically a ratio of the GPDE and GPDH. And so if these two functions behaves in the same way in the small x region, then this ratio is roughly proportional to the skewness. And you can see it goes like it's proportional to the skewness. And so that's why, and here's a skewness of this experimental data. So in this peak region, the skewness is large, but in the high energy region, the large center mass region, the skewness is small. So you can see by measuring this decrease of the A sub n as you decrease the skewness, then you can get information about the small x behavior of this GPDE. So the coming data from Rick, or maybe in the future data from EIC, may be able to constrain the small x region behavior of this GPDE. All right, so in the last 5 minutes, I want to talk about EDM. So I completely changed gears in the last 5 minutes. So this is a very bit exotic topic for probably for you, because this is usually a low energy physics, and I want to talk about this in the context of a high energy spin physics. So EDM is, this is a pattern from Wikipedia, that if it's non-vanishing, then it's a sign of the CP violation. And of course, we know that the standard model violates CP, but that's the prediction from the standard model is too small. It's too small, much smaller than the current experimental upper bound of the EDM. So you can see this upper bound as a function of the time. And so the upper bound goes down as a function as the years goes on. But it's but the standard model prediction is much way below the current upper bound. So there is an interesting possibility that some physics beyond the standard model has a CP violation, and that induces a large EDM. And the one thing that we can point out that EDM is a vector, so it's a dipole moment, it's a vector, and so it must be proportional to the nucleon spin, right? The spin is the only vector in the proton. So if there is a EDM, it must be proportional to spin. So it is related. So the EDM is related to spin physics. So here's the definition. So this is an electromagnetic current in the proton matrix element. And usually you have a Dirac and a Pauli form factor, F1 and F2. But if CP is violated, then there is a third form factor, which I call F3. And this value at vanishing momentum transfer Q squared is equal to 0 is proportional to the electric dipole moment. And there are several scenarios of beyond the star model that can induce EDM, and one of them is called the Weinberg operator. So this is a dimension 6 CP odd operator, which can be induced in the QCD Lagrangian in certain scenarios of beyond the standard model. For example, if you have these gluinos and supersymmetric particles, then you have induces the 3-gluon coupling, which is violates CP. And so this Weinberg operator can be induced in the QCD Lagrangian and with this some coefficient W. And we don't know, of course, we don't know this W. This is determined by the beyond the standard model. But once we know W, then you can determine the induced electromagnetic moment. So this is the proportionality constant between EDM and W. This is a 100% QCD problem, which we should be able to answer that in QCD. And of course, there's a large QCD calculation, but this is a dimension 6 gluonic operator. It's a nightmare for the largest QCD. So it's not yet practical. So that's why we need some phenomenological insight into this problem, and even an order of magnitude estimate is useful actually. So, so what I did is the following. So first, I derived this identity, which I think is new as far as I know, but yeah, okay. So I derived this identity. This is the operator identity. From on the left-hand side, you have this Weinberg operator, and on the right-hand side, we have some dimension 6 gluonic operators. And if you take the matrix element of this operator, the proton matrix element, then from this first term, I get this dimension 5 operator. So there is a total derivative, which turns into a momentum transfer delta. Then what remains is the dimension 5 operator, which is actually familiar to the experts of the QCD spin, because the matrix element of this dimension 5 operator is actually enters the twist 4 correction in polarized DIS. So if you measure this G1 structure function as a function of a Q square, then in the first line, you have this delta sigma, which I talked about. So usually people are interested in this delta sigma. This is how you derive this is how you determine the delta sigma from experiment. But if you go to the higher twist, the second line, which is suppressed by 1 over Q squared, then this parameter F0 is actually proportional to this matrix element of the polarized of this Weinberg operator. So we have some connection between this Weinberg operator and this parameter F0. And so, but there's another operator in this. If you look at this identity, there is a third operator here, and we don't know the matrix element of that. However, we can get some insight into the relative magnitude of this matrix element by looking at the evolution of these operators. So we have 3 operators and 1 relation. So there are 2 independent operators, and we can talk about the mixing between these operators. And so we basically we have a 2x2 anomalous dimension matrix. So the 1-1 component, this is the anomalous dimension of the Weinberg operator, which is computed by Morozov 6 years before the Weinberg's paper, actually. And there is a recent calculation of the 3-loop anomalous dimension for this Weinberg operators. And this this twist 4 operator that appears in polarized DIS, the Weinberg, the anomalous dimension was calculated by Shuriak and Bernstein. And this is gamma 4. This is known for 40 years, but its off-diagonal mixing entry is not known. So I calculated, and this I got this result. So from that, we can study the mixing between these 2 operators, and we can get the relative magnitude. We can get some insight into the magnitude of the matrix element. And that's what I did. I skipped the details, but basically the EDM is proportional to this matrix element of this Weinberg operators. And from this operator is related to this F0 parameter. In this way, this is just an estimate. And I took F0 from this instant model. Ideally, I want to use the experimental value, but right now we don't know the experimental value. So I basically took the model calculation from instanton, and I made this estimate, which is consistent with the other estimate from the other estimates. So this is a new connection between EIC spin and the physics beyond the standard model. And so I think it's a quite a challenge to measure this F0 parameter because it's a higher twist effect, but given the EIC's large level arming Q square, it might be possible. So that brings me to the summary. So spin is one of the core sciences of EIC, and I talk about the Jaffe-Manhasm sum rule. In that, the orbital angular momentum is the key to fulfill the spin sum rule, and that's not, the progress is so far quite limited, but there is a glimmer of hope. And transverse spin is the main objective single spin asymmetry, and what is the origin of the single spin asymmetry. And I talk about the global analysis and also the new mechanism. Well, it's not new, but it's a Patavati-QCD mechanism, which is renewed, the revival of the Patavati-QCD contribution, and also talk about the GPD and the challenges, associated challenges. Okay, so thank you very much. That's all.
Thank you, Yoshitaka, for that very comprehensive talk of the spin physics opportunities at the EIC. Let me clap in behalf of the audience. Okay, so now we have some time for questions. I see Xiongling has a question. Please unmute yourself.
Okay, I have several simple questions. So first, thank you very much for the talk. And the first one is, does the BFTL for the GPDH include the gluon saturation? I think it doesn't, right? So why it agrees with your calculation, which includes the gluon saturation?
What do you mean? You're talking about this slide?
The previous slides, this and so does the BFTL for the H include the gluon saturation?
Yes.
Or it includes the saturation, right?
So this is unpolarized gluon distribution function, which is sensitive to the gluon saturation. This is standard. I'm not sure what your question.
Oh, my question is, does the gluon saturation included here for the BFTL equation?
Oh no, sorry, no, not at the BFK level. Yes, BFK there is no saturation. It's just twist two physics. But you can also include the effect of saturation, like so this is the equation for E, but I have an equation for G, and that's a usual Walensky-Kovshev equation. So there is a saturation.
Okay, thank you, Dorothy. So for the small x behavior, it doesn't include the saturation here, right?
Well, this is a BFK, so there is no saturation at this point.
Okay, got it. Thank you. And my second question is back to the delta G you taught at the beginning. So I'm a little bit curious about the exactly zero delta G. We add it exactly zero, so it will get some contribution from the gluon topology, but the experiment can never measure it. So my question is, will the lattice QCD calculation include the gluon topology contribution to the delta G?
What do you mean by topology? Are you talking about the instantons?
Yes, the instanton. So the delta G for the x equals 0 might get some contribution from the instanton. I read from some review at least. So I don't know whether, because the experiment can never reach x equals 0.
Right.
So I'm curious about whether lattice calculation can include such effect for x equals 0?
Yeah, so there's a lattice measurement of this total delta G. So it's integrated quantity. There's a lattice simulation of delta G. Yeah, so there is a paper by Kentucky group, but I don't know if the topology is how they deal with the topology, because I think it's challenging to explore all the topologies, right, in the lattice simulation. But I'm not an expert of that. So, but there is indeed a lattice simulation of delta G.
Oh, okay, got it. Thank you. My last question, naive question is, you mentioned the delta G and the LG will cancel with each other. So, if so, why they will cancel for the small x part of the delta G and LG? So maybe the remaining part is canceled exactly, or there is. So for the dark spin you measured, it may come from the small x delta G and the LG, but you also mentioned they will be canceled. So they will be canceled very cleanly, very exactly, or there is still a large remaining which canceled not very well and contribute to the final non-zero net result.
Well, this is not the exact cancellation. You can see this ratio is not 1. So alpha is between 0 and 1. So there is not exact cancellation. So the orbital angular momentum might be even larger than delta G, at least from this estimate. And so that's one thing. But on the other hand, the total delta G, this is a fundamental quantity, right? So this is a fundamental quantity of the proton. So we are interested in the value of that. So simply measuring delta G, that's a very important problem of the EIC, right? Independently of these cancellation arguments, just measuring delta G, that's important. It's a fundamental property of the proton. And in addition, but I'm saying that this is not enough because of this cancellation. So we should really look at the orbital angular momentum. That's basically my message.
Okay, got it. We need to separate of them. Okay, thank you.
Thanks, Shunling. Now, Feng Yuan, do you have a question? Please go ahead.
Yeah, Yoshi, very nice talk. And can you go back to the Sivers effect and see this? I think you have summarized slides there.
Like this?
Yeah. So one of the question, of course, is that the Sivers, okay, Sivers contribution to this asymmetry really depends on TMD. So I'm wondering, is any other term in this expression also have TMD?
Oh, so all these terms are TMDs. So these are all TMDs. Okay. So F1T and
no. The point for example, if you apply TMD evolution, right?
Mm-hmm. So
I don't know how you do that if that contribution only happens at alpha S square order or alpha S.
So the other terms, so of course Sivers is the leading term. The other terms are either 3 TMDs or higher order in alpha S. Okay, so they are in some sense suppressed, except maybe this G1T term that's the first term on the second line. And that is the TMD analog of this effect that I calculated. So if you can see, if you go to the small PT, and then asymmetry basically increases, and that's because the asymmetry goes like 1 over PT. So if you go to a smaller PT, then asymmetry increases. So I would expect that the even larger asymmetry from the TMD analog of this mechanism. But we haven't done the numerics, but this term might be important, the first term on the second line. And the other terms, I don't know. They are parametric of the higher order because they're either 2-3 or higher order in alpha S, but the numerical impact, I don't know.
No, my question, of course, concerns the resummation effect. I mean, if you do have F1T probe and G1T, right? You say you argue that this actually is a TMD. So the resummation one comes in, right? So yeah. So in a sense, for example, G1T and F1T probe will give you similar behavior,
Mm-hmm.
I mean, of course, depends on what kind of function, what the Sivers function will be and G1T will be, right? And if you do, if you apply TMD resummation, in the end is similar. So they all depend on TRIS3 quark-gluon correlation function. But the G1T will have additional upper S suppression because H2 dependence there, right? So I mean, they of course maybe it's okay. I'm just curious how you do the TMD resummation for the rest of this.
We don't know the TMD resummation for this G1T. Is this known?
Yeah, because G1T is the leading interest TMD.
Oh, really?
The resummation is similar to F1T per. Okay,
yeah, okay. Okay, maybe then we can doable but we haven't calculated this hard part. This is going to be very tough. Yeah, so we haven't done that yet. But
anyway, it will be very interesting to look into this into detail.
Yes, we want to do that, but we need
I just want to mention that Werner and I have been thinking about how to do resummation for higher trace terms in Julian, and also probably also apply to here too.
Okay, very good. Okay.
Yeah. Just one last clarification. So you mentioned about the gypsy and rig. I guess you mentioned UPC. That will be PA, right?
Yes. So the STAR collaboration, they are going to measure in 2024 this process, but this photon is coming from the nucleus. So this is an ultra-peripheral collision. So this photon is real. And that's why this energy, center mass energy, is limited to.
Okay, so this depends on this star. We're going to have a PA run. It's not guaranteed, right?
Yeah, there will be a PA run.
There will be a PA run, but we don't know how long. Star request, I think, 11 weeks. And we may not get 11 weeks. Yeah.
Okay.
Does S-Physics also have PA run?
I think so, but they don't want that long. That's the conflict. Yeah.
Okay, gotcha.
Yeah. This is round 24, so not the current one.
Yeah. And also, of course, you can measure this process at the EIC, and this is really DIS, and then you can go to the higher W, and then maybe you can study better this small x behavior, because higher W means small x.
That's right. Very good. I don't have any more questions. Sorry.
Thank you, Feng, for the question. Does anybody else have any last question for Yoshitaka? Please raise your hand. I have one more question, maybe of a very different character. So in this talk, you mostly focus about the proton spin structure, but the EIC one can also polarize light ions. Is there any work in this direction in the spin of light ions?
Yeah, there must be, but I'm not familiar with that. I think there must be a work on deuteron spin and also maybe helium spin, but okay, sorry, I'm not familiar with that.
Do you expect any tangible connection between the themes that you have discussed today and that community spin of the light ions like deuterium, or is are they using very different methodology?
Yeah, it's a different type of physics. For example, you can measure this polarized EMC effect, for example. That's another topic, but it's not so related to what I talked today, but they are interesting on its own right? And also, if you have a spin one, if you have a deuteron which is spin one, then you have a new structure functions. that might also be interesting.
Mm-hmm.
But I'm not familiar with. I'm not following the recent work, so I cannot say much.
Maybe I add a short comment. So for the neutron hidden stray, that's definitely target on the main focus will be to get the neutron spin structure, or in a sense try to understand flavor dependent of the polarized quark distribution.
Yes.
For both longitudinal and transverse. I mean, of course, you should also mention about because the spin one particle neutron, there's additional B1 asymmetry and so on. So it's very interesting. For the polarized, for example, I don't know if that's already on the schedule on the discussion of yellow report. For example, polarized lithium or night ion will provide additional information on the EMC effect. The polarized EMC effect will help us to pin down the physics mechanism for the EMC effect. So that's one of the important things they can do.
Yeah, thank you.
Okay, great, thanks. Okay.
All right.
So thank you very much, Yoshitaka, again for the nice seminar, and thanks all the participants for attending and for the discussions.
Yeah, thank you very much.